joined so far. We are pleased that you're able to participate in our fourth quarter webinar series by the STEM Leadership Alliance. We are in for a spectacular presentation today by David Graver. So we'll get started in just a moment on that. But I do want to let everyone know that we do have people that are attending this from around the world. So that's why we did set it at this later time during the day so that we could have our friends from Nepal, the Philippines, and all of Southeast Asia to be able to join us as well. So I know we'll just give it probably another, maybe 30 seconds or so, just to allow people to come in. We will have this recorded. I will be sharing this back out as well. And we will have it on both the STEM Happens Network and the STEM Leadership Alliance websites as well. So let's just give it another 30 seconds here, and then we're going to take it away. All right, David, I am going to go ahead and turn it over to you. I first just want to start by welcoming everyone once again for joining us this evening or this morning. So wherever you are in the world, we just want to send well wishes to you. We're going to talk about unpacking the next generation science standards. And David Graber here with us today is not just going to talk about the three dimensions of the next generation science standards, but also hit upon the literacy component that's so incredibly important when we talk about the next generation science standards that focuses both on the engineering, science, ELA, math, but it's across all the content areas. So we're looking forward to this conversation here. If you do have any questions, though, please don't hesitate to post in the chat or in the Q&A section. So the presentation will run approximately 45 minutes, and then at the end, jot down any questions that you have. And then at the end, we'll definitely be opening this up for Q&A so that we can just make sure we're addressing any concerns, questions, thoughts that anybody has about this session today. So with that, David, I am going to go ahead and turn it over to you, and let's get started. Thank you, everyone. And you just, yep.
Okay. Good morning, good evening, or good afternoon, depending on where you are. Happy to see you all today. Thank you, Kelly, for the lovely introduction. I'm very much looking forward to kicking off this series this evening and taking a deeper look at the next generation science standards and leaning forward into how those standards can work across all curriculum areas to enrich students' educational experiences. Today, we're going to start with taking a look at not only the three dimensions of the next generation science standards, as Kelly so aptly described, but we're also going to go a little bit deeper and look at not only the cross-cutting concepts, but how it ties deeply into disciplinary literacy. And that doesn't just mean ELA. So I'm going to now lean us forward. So we're going to take a look, like I said, at the three dimensions of the next generation science standards. We're going to look at the performance expectations. We're going to look at the conceptual shifts that are represented inside the standards themselves. And we're going to take a nice dive into some disciplinary literacy work. And then we're going to share some resources out. And Kelly and Dr. Fernandez will come back and share a lot of the great resources that the SLA has available for you. So before we begin, as a little bit of an icebreaker, okay, I'm sharing. So Kelly and Dr. Fernandez, I'll just ask that you, if you see people's hands up, just to acknowledge. But one thing I want to hear from some of the folks on the call right now, really briefly, we'll take 5 minutes, is introduce yourself, where you're from, and tell us one thing you know for sure about the next generation science standards, one brief question that you have about the next generation science standards, and how you think the next generation science standards are different.
And if everyone just wants to go ahead and put that in the chat, and then I'll monitor that for you, David.
Even better. That's perfect. Okay. So while you're thinking about that, I'm going to leap us off into thinking about what these conceptual shifts are. So that can help you answer some of the questions that we just asked. So some of the shifts are is that the K through 12 science education really needs to reflect this interconnectedness across the nature of science as it's practiced, but not only practiced it, but experienced in the real world. They should also not be viewed as curricula, but as student performance expectations that should be embedded within curricula. And that curricula could be across multiple areas. The science concepts in the next generation science centers are vertical. They build coherently from kindergarten all the way to 12th grade. They focus on a deeper conceptual understanding of the content, not just the application of the content. Cannot have one without the other in the next gen science standards. We also see a verticality in science and engineering and how they're integrated throughout the standards all the way from K through 12. Oftentimes, and that I just want to make a quick point here is that, engineering, in particular, standards for engineering often aren't seen until later in a student's curricular experience. So it's nice that we are looking at it vertically from kindergarten on up. The next generation science standards are also designed to prepare students not only for college, but for career, technical career, and citizenship. And the Common Core state standards and the next gen science standards, they're aligned. And we're going to take a deeper look at that into why understanding the concept of disciplinary literacy is really, really important. So these are some of the shifts that we should be focused on when we're rolling this out across schools, across classrooms, is really understanding that there's some shifts that we have to, take note of. And as we're trying to apply this work, make sure that we understand how these shifts get applied. So that's what we're going to be looking at a little bit here. But again, the three dimensions of science learning are critical to really unpacking this work. So a quick overview is that within the standards themselves, there are three distinct and equally important dimensions that we're going to look at both visually and you're going to hear from me. Now, these dimensions are combined to form each standard. So you're going to see these dimensions in a standard, right? Which is, we're going to introduce a term called cross-cutting concepts, right? I'm sure you're familiar with, but that's where that idea lives. And each dimension works with the other two to help students build a cohesive understanding of that particular concept. In reading instruction, there's a reading rope, and as we can see the stuff intertwining. In writing, there's a writing rope, etc. So here, it's really how these dimensions work together. And here's what they are. They are cross-cutting concepts where we look for patterns, and there are 7 different concepts. There are patterns, cause and effect, scale, proportion, and quantity, systems and system models, energy and matter, structure and function, and stability and change. So these 7 concepts cross-cut. There are 8 science and engineering practices, and those are, and I ask you to open your mind beyond just science and engineering, but thinking about these practices across any subject area in particular, is asking questions and defining problems, develop and using models, plan and carry out investigations, analyze and interpret data, use mathematical and computational thinking, construct explanations, and design solutions. All this is around science and engineering, but again, expand that, into other areas as well. Engage in argument from evidence, obtain, evaluate, and communicate information. And then there's the core ideas, the disciplinary core ideas, and we're going to call those the DCIs going forward. But those are physical sciences, life sciences, earth and space sciences, engineering, technology, and applications of science. So these are the 3 dimensions, often represented by those 3 ribbons in the top left of the screen: practices, core ideas, and cross-cutting. You'll see that all the time when they're being represented within the standards. So as I was using that rope analogy earlier, right, you can really get a visual here of what those three dimensions and how they kind of weave within one another throughout the the elementary, middle, and high school cycle, right? We've got the performance expectations. The framework requires contextual application of the three dimensions by the students and focuses on how and why as well as what. So, right? Practices, weaving through the ideas, cross-cutting concepts, cut exactly as they're defined, cutting across the different concepts, and learning and using this framework contextually to apply it to any kind of problem that teachers might be utilizing within the class. And we want to also know the how, the why, but also the what. And I use those terms very specifically, as we'll get to a little bit later, right? Those are usually terms we hear in English classrooms, right? Like who, what, where, when, and why. So it's, as you can see, again, things cut across different subject areas very, very casually sometimes, but intentionally. So what are the performance expectations? Going back again, I was talking about these performance expectations. These are what state what the student should be able to do very, very succinctly in order to demonstrate that they have met the standard, providing clear and specific targets for curriculum instruction and classroom assessment. So those performance expectations, again, are not curricula, but it's critical to utilize them in developing curriculum or developing or adapting or adopting curriculum, whichever your district or your school is engaged in. Now, the performance expectations build across the years, right? Starts with K through 2, elevates up 3 through 5, significantly more depth in 6 through 8, and the complexity that we see in the 9th and 12th grade. As you can see in the standards as we'll look, right? So 2nd grade, physical science, standard 1.2, analyze data obtained from testing different materials to determine which materials have the properties that are best suited. Now we see how this escalates into the upper grades in elementary school. Make observations and actually do this, not just analyze the data. Now it's analyze, interpret, and getting deeper. Now it's just not about making observations and measurements to identify materials, but it's analyzing and interpreting the data of the properties and substances before and after the substances interact to determine if a chemical reaction has occurred. So we're moving from, right, into more chemistry. And as we get to, right, use the periodic table as a model to predict the relative properties. So you can see how the performance expectations are vertical, as I described before. So it's important, and you'll notice, again, they all can be identified by the PS, 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 PS1 across any grade. So you can, even though they live there, 1.2, 1.3, 1.2, 1.1, there are different standards that connect across different grades in different ways. So it's important to follow this vertical trail and see how the kids that not only that you may be teaching are going to be working with a particular standard, but also how the kids that are where they're going to go next and how they need to utilize the next level of that standard in their coursework to be successful. So the verticality piece is really critical. The science and engineering practices that we looked at, right? These describe what scientists do. This is what they do. This is how they investigate the natural world. This is what engineers do to design and build systems. Practices are there so that they can better explain and extend what is meant by inquiry in science and the range of cognitive, social, and physical practices that it requires. They engage in practices to build, deepen, and apply their knowledge of core ideas and the cross-cutting concepts that are inside the standards. They utilize the scientific method. They make an observation, state a problem, identify the variables involved, formulate a hypothesis, design experiments to test the hypothesis, collect the data, draw a conclusion, sometimes going back right to the beginning and running through the process 1,000 times before an accurate conclusion could be drawn. But how are the practices integrated into both inquiry and design, right? And this is where we're going to start to connect deeper to the literacy component and really understand how these standards aren't just science standards. The three spheres of activity for scientists and engineers, right? We've got to argue, critique, and to analyze, right? That's what they do. Analyze, critique, argue, different theories and models, how they impact the real world. They collect data and test solutions, formulate hypotheses, and propose solutions, all the while evaluating, investigating, deepening explanations and solutions, asking questions, observing, experimenting, measuring between the real world to play with that data and to understand different ways data is different in different situations. We use theories and models to imagine, reason, calculate, and predict so that we can generate hypotheses that make sense, that are worth pursuing, so that we can land to a solution. Now, investigation and inquiry is the dominant activity. Ideas to the evidence are analyzed, debated, and evaluated. We have to evaluate. And you can see how this works in lots of different directions, because sometimes we find data in different stages. We want to construct and explain or design using reasoning, creative thinking, and models. So there's so much at play here beyond just science. It's taking the scientific method and then positioning it so that it can be understood and communicated. And that leads us to the cross-cutting concepts. And these are the vehicles within the standards that help students to explore the connections across the 4 domains, right? And as I was saying in the verticality before, how standards sometimes leap around and connect to other standards. This is what I'm talking about, right? So there's things in physical science that connect to things in life science, that connect to things in earth and space science, and ultimately engineering loops through all of them, because we have to build things to help solve some of these problems. Think about colliders. Those this giant what's it called, the one in the CERN Hadron Collider, right? Think about the size of that and the engineering that needed to go into that to discover. Let's think of these concepts as themes. These are the concepts that bridge the disciplinary core boundaries, having explanatory value throughout much of science and engineering. So this is where everything comes together, right? Patterns and causality. We look for patterns. We look for cause and effect, relationships, and all the while looking for structure and function within the patterns. We need systems and models. We know those systems and models have to be designed to react to stability and change. We have to monitor scale, proportion, and quantity, the data, and energy and matter. I'm not going to read these to you, but just, we have to understand that the patterns, they appear across nature and science. Look at the symmetry of flowers or the lunar cycle. We can find different areas of science here, right? So there are patterns. They need to be able to not only recognize patterns, but ask questions about why they occur in nature. I can immediately start to draw connections to other subject areas, thinking about things like the Fibonacci sequence and things to that effect, right? We've got cause and effect, which is mechanism and explanation. This is the concept that helps students when planning and carrying out the investigations or designing and testing the solutions. seeing what happens, right? Taking the leap of faith. And a big part of investigating different phenomena involves comparing them using relative scales and describing them using units. So we need scale, proportion, and quantity, right? Many of this phenomena students study in different schools and classrooms are at a scale either too small, sometimes we need microscopes, right, or too large to observe, and models can be used to make sense of them. Think about the project everybody does back in the elementary schools when they build the solar system with the foam balls or the aluminum foil or using fruit, right? I remember doing that to this day. One of the most fun experiences I had in the classroom when I was a kid. The systems and models, this makes the world easier to investigate, right? System models are useful tools for studying how a system behaves within itself, how it interacts with other systems. So you have to be able to work within systems or build systems models. Energy and matter flows in and out of any system. We know that, right? So sunlight and water that the plant needs to grow, or the flow of water in the Earth's atmosphere. We have to be able to observe and model these flows and cycles so that we can understand the overarching reasons for why things happen. Structure and function, shapes, relationships, and properties of materials, understanding the structure and function of different materials to help engineers create and move forward. Stability and change is the final cross-cutting concept. And this is, understanding concepts like dynamic equilibrium, where stability of a system depends on constant change. For example, how a water flows through a dam, or how the moon's orbit around the Earth changes and affects the tides. Now, those cross-cutting concepts are then dialed down into the disciplinary core ideas that students need to learn and how they need to learn them vertically, right? So they have a broad importance both within and across multiple science and engineering disciplines. They build on each other as students progress through the grade levels and are grouped into the following 4 domains, as we mentioned: physical science, life science, earth and space science, and engineering. So let's take a look at each one of them really quickly, how they're kind of organized within the standards themselves. As you can see, there are 4 life science DCIs, again, disciplinary core ideas. There's life science DCI 1, from molecule to organism, structures and processes. I'm not going to read them to you. They're right there. But you can see these are the disciplinary core ideas that need to enter the curricular world, right? As we start to hit on the core ideas. But they're organized very effectively so that curricula can be designed using the standards. Because remember, these aren't the curricula, these are just the drivers. And they're in the 4 areas, again, are life science, physical science, earth and space science, and engineering and technology. Let's take a look at how they work out vertically, right? So life science starts with looking at interdependent relationships in ecosystems. For example, how do animals and plants interact within their environment? Structures and functions and informational processing. In 2nd grade, we move to independent relationships in ecosystems. In 3rd grade, we hop back to that interdependent relationship within the ecosystems, but looking at how the environmental impacts they have on organisms. We look at inheritance and variation of traits in terms of life cycles and traits. Structure, function, and information processing in the 4th grade. And matter and energy in organisms and ecosystems. So you can see those cross-cutting concepts, right? Even in how the disciplinary core ideas are drawn out, right? I immediately started thinking about the flow of energy, etc., and the systems within us to help us observe them, etc. Now, once we get to middle school in the life science area, we're going to look at structure, function, information processing. Again, I'm not going to read these to you, but you can see these 6 areas of study, these disciplinary core ideas, need to be focused on in the 6th, 7th, and 8th grade in the most natural order possible. This is not a given order. However, you want to, when you're designing curricula based off of these disciplinary content ideas, right? These are the ones. These are the high leverage topics. These are the disciplinary core ideas. And in high school, same piece. But again, you can see how they work vertically. Interdependent relationships and ecosystems is the theme we started with in kindergarten, if you recall. Traits was in 3rd grade. So it's cyclical, right? But it gets more and more complex. The core idea goes deeper and deeper and deeper as kids get older and older and older and learn and learn and learn. The physical science, you'll see the same kind of mirrored sort of articulation up as we just saw. Starts with structures and properties of matter, moves to waves, light and sound. Again, I'm not going to read them to you. You can see them here. But again, structures and property and matter come back to that in 5th grade, because that's going to be the bridge to get into it deeper in the 6th grade and middle school, where we look at physical science across the same. Now we introduce chemical reactions, forces and interactions, waves and electromagnetic radiation. We go deeper in the middle school area. Engineering design, again, cross-cutting concept, right? As we get to high school, again, you see, we just compound and get deeper and deeper and deeper. So the vertical nature of these disciplinary core ideas is really makes for a deep, deep conceptual understanding from kindergarten to 12th grade. So gone should be the idea of there's too much to teach. This is very focused. Earth and space science, weather and climate, patterns and cycles of space systems, etc. I'm not going to read them to you. You see how they scaffold up kindergarten, 1st, 2nd, 3rd. Kelly will be sharing this out to everybody. So again, you know, right? Middle school and high school, as you can see again in this one, right? So in all of the disciplinary core ideas, we see the cross-cutting concepts. We see the verticality, so that we can really deepen the impact and the conceptual understanding for student learning around the ideas that are central to being scientists. So what's our job here now, right, is to really find where these disciplinary literacy connections live within these standards. So we ask you if you're ready, as in reading, evidence, and argumentation in disciplinary instruction. Let's take a look at a standard. We're going to take a look at a standard. It's middle school standard. We'll work in the middle, right? Elementary, middle, and high school. So we'll just work in the middle, for example. You'll notice these are the actual next generation science standards. And I circled very, very clearly, even though these are science standards, we can see how they call out and immediately themselves ask for us to construct a scientific explanation based on evidence, which sounds a lot like an ELA standard to me. But when they also do is they connect it, right? You can see this is still the science standards, but they make a common core standards connection. And they show you the actual reading and literacy standards and the writing standards that are going to need to be connected here. So the standards themselves were built knowing that even though these are science standards, this is important, right? And this is going to play in a moment, right? So really, we think about this in terms of a theory of action for the standards themselves. So for example, if the student is going to be constructing a scientific explanation based on evidence, which is a core idea, then we must cite textual evidence, which is to write arguments or write explanatory text, which means we must work with literacy, right? So I'll just give you another example of how math, because remember, disciplinary literacy is not just about reading and writing. It's also about mathematics, right? It could be about art. It depends on the discipline that's being integrated. Here's an example where mathematics, right? So you can take a look. Again, the standard itself is embedded with literacy. Construct an explanation, construct an argument. It also makes the same connection to the mathematical practices. So not only does it connect to the Common Core standards for ELA and literacy, but also for the mathematical practices in the Common Core. Right? And this is a nice chart. This is for your reference more than it is to review right now, but you can see the mathematical practices that are in the Common Core state standards, okay, which are pretty much, work across the world. And you can see the science and engineering practices and how they align with one another, right? Like, so for example, I won't read all of them to you, but I'll give you one example. Making sense of problems and persevering in solving them can be seen in the science and engineering practices through asking questions and defining problems, or planning and carrying out investigations. So you can see the alignment across the board here, right? And not only can you see it in mathematics, but you can see it across the science and the ELA standards, right? So this is a really nice chart to unpack with your schools, with your districts, to help see the cross section of learning that happens by using these next generation science standards, which are really incredible, right? So let's take a look at a really nice way to see how they intersect, right? So this is another great visual that you can utilize when unpacking the standards with your respective school or district, right? So you can see across the middle, there's ELA standards, math standards, science standards, all connected, right? We're obtaining, synthesizing, and reporting findings as an ELA standard, but that sounds a lot like science you're right? Using appropriate tools strategically. Again, that could be an engineering as well as a mathematical concept. So you can really see how the commonalities among the practices in science, math, and ELA really work together, and how the next generation science standards really call them out and force schools and districts and classrooms to really highlight literacy. And it's going to lead us to a problem that we're going to try to solve in a moment, which is sort of unpacking this term of disciplinary literacy. We're going to take a little bit of a closer look. Again, I'm not going to read this whole thing to you, but there's a difference between basic literacy, intermediate literacy, and disciplinary literacy, right? And so real quick, right, obviously basic is basic, general basic skills, decoding, grammar, basic facts, looking up vocabulary words, etc. Then there's emphasis on text-based practices, which is intermediate literacy, which is we're extracting information from a text, right? Reading more complex texts over time, related discourse practices, but not specialized to any specific discipline. Just being able to navigate complex text and make comprehensive meaning of them. And then there's disciplinary literacy. And disciplinary literacy, it frames instruction for students to address authentic questions about their community and individual lives. It prioritizes authentic work of the disciplines themselves. It values the complexity of knowledge systems. It attends to issues of equity, power, and justice. So it's really, it's not just a hip name for content area reading, okay? I want to just, we talk all the time about how science teachers are also teachers of reading, or history teachers are also teachers of reading. We know that there are teachers that must utilize reading in order for students to comprehend the depth that they're trying to get them to comprehend at. But middle and high school teachers in those disciplines, in both science and even social studies, were trained not as reading instructors. So I'm going to back up a little bit here and just talk about a problem that I know as having been a principal and having been a deputy superintendent, seeing across time that when kids go from elementary to middle school and when kids go from middle to high school, I often hear the principals of receiving students saying, why am I getting kids who are performing so low in ELA? Why? Well, what happens is that when you rewind the tape all the way back to elementary school, when we move kids from second to third grade, what we're really doing is moving kids from learning how to read in grades K through 2 to reading to learn in grades 3 through 12. Now, that's a much larger curve in reading to learn, so that obviously takes a lot longer and to utilize those tools. But what happens is when kids fall behind in grades K through 2, they're immediately 2 to 3 years behind once they get to grade 4 or grade 5. And what happens is, right, is we land in a situation like this. Has anybody seen this article? The elite college students who can't read books on the cover of this month's Atlantic. Okay, for those of you international, it's a national news piece that comments on the state of affairs in the country, and it's really it's focused on the elite college students at Harvard, students at Princeton, the most elite academic universities, and they've polled professors, and kids are not able to read the text when they get to college. So we can see this perpetuating itself all the way up through college, right? The kids aren't able to decode text enough to do much with them. So what are the instructional responses to literacy development that have gotten us to this place? Like, how does this happen, right? How did we get here? And what we know is that adolescent literacy, we look to remediate, right? We look to go backwards instead of pushing forwards. We do iReady, we achieve 3000, we use Maya, we use all of these different remedial, and these programs are excellent and often needed. I'm not saying we shouldn't be using them, but this is what we do, right? And we administer large scale assessments, and we identify student needs, and we do all the data and the needs assessment. We require oftentimes that students trade in an elective, a phys ed class, that movement that's necessary, art or music, right, for an intervention class, so that they can stay on track, so that when they get to the next level, they're ready to go. But it's basically elementary school continued. And so we're perpetuating the problem rather than solving the problem, right? We're basically looking at adolescent literacy as an extension of primary grade literacy, which is not the case. Remember how I told you, we went from learning how to read to reading to learn, and that reading to learn gets way and way more complex as we get up through the grade levels, right? We also know that we support in the disciplines with our literacy coaches, because what else are we going to do as a school? We need to use our people that are trained in literacy to help our folks that are not trained in literacy get up to speed on literacy instruction. So what we wind up doing is we wind up using literacy across the content areas, or all teachers are teachers of reading, right? We provide training for teachers on how to teach reading using content area instructional materials. This is how we respond, right? But what we can see here on the bottom is that there are two separate things. Content area reading is one thing, and disciplinary reading is a whole other thing, right? We use generalizable skills and activities that can be used in all reading in the content area reading model. KWL charts, SQ3R charts, the Frayer model, all excellent strategies, all research-based strategies that are effective. But these are very generalized skills for reading in any area, right? Summarizing, using graphs to help break down, to summarize the text. But in disciplinary reading, those things take on whole other agendas. When you look at a table or a chart in a scientific piece or a historical piece, they take on much deeper meaning than they do in a fiction piece, or a biography per se. We look at the observe, infer, conclude model. Is the information causal? Is it relational? Is it hierarchical? So like the way that these two readings happen are totally different. So our response of literacy across the content areas isn't helping, right? Because we don't understand this disciplinary literacy. In short, in content area reading, we're using reading and writing to study and learn information. If you walk out of here with any definition of disciplinary literacy, this is what I want you to remember. In disciplinary reading, we must ask, how does literacy help us make meaning within a discipline? So my science teachers who aren't reading teachers, true, you are not reading teachers, but equally true is you require your students to be able to read and write in order to communicate their understanding of what you're trying to teach them. So you do need to lean on literacy and do need to understand how it applies to your specific domain. This is a nice comparison across the two. One is on the focus on learning from the text. The other is specialized problem areas, right? Major emphasis on literacy learning, tools, response journals, reading logs, right? Here we need, corroboration, nominalization. We need to turn processes into nouns in disciplinary reading, right? The idea in content area reading is not to read books like a chemist, but to know how to study books, including chemistry books. But decoding them, right? We know we need to annotate text, we need to use the margins and take notes. All those different strategies that we learn in content area literacy. They're not invalid, but we need to also elevate to understand that we're focused on specialized problems in a very specific area where the tools of reading are different than the tools of reading in general text. Imagine not knowing how to corroborate something in today's day and age when trying to sort through. I mean, we're, in the United States, we're in the middle of election season, right? And so people are reading to try to figure out who the best person to vote for is. You need to be able to corroborate your sources. That's a totally different kind of reading than is reading your favorite book on a Sunday afternoon. It's two different things. Now, the way that these things manifest themselves are through the use of phenomena in the NGSS, right? So the instructional materials really need to tap into phenomena-based things that students can investigate and read and write about, design experiments around, engineer solutions for, right? So what we're going to do is I'm going to ask you almost for homework for the next session, because we're about to wind down tonight's session, is I want you to think about these three things. I want you to think about what comes to your mind when you hear the word phenomena. What does phenomena have to do with the next generation science standards? And what does it actually have to do with science education at all? So I'm going to leave you with that as food for thought, right? And just sort of give you a quick cheat code before I give it back to Kelly and Dr. Sal. But a phenomenon is basically an extraordinary occurrence or circumstance. For example, in the 50s, rock and roll, and you thought I was going to talk about a volcano, right? Because you saw it in the Northern Lights or something like that. I'm talking about rock and roll. It was considered a new cultural phenomenon. But today we think of crop circles as a mysterious phenomenon. So there's lots of different phenomenon out there that we can ask us to investigate. But it's taking a look at something that's happening, that's impacting our world, whether for better or for worse, and how we can help it or fix it or solve it. So the way that I want you to think going forward is phenomenon leads to a project that we can use in the classroom to help kids find solutions. And with that, I turn it back to Kelly and Dr. Sal, and thank you all for your time this evening and hope that was helpful for you.
Well, thank you, David, so much. And I think that's one of the key takeaways, in my opinion, on this is really understanding that when we talk about the next generation science standards, we're not only just looking through the lens of science, but how it truly looks at all disciplines, how you connect those disciplines. But even more importantly, we have to get into this literacy component of it. We have to understand when students are looking at this content, and science is just so rich in terms of terminology and all of this good stuff that it has in there. But if students can't comprehend this to that fullest level, then they're just glazing over the words and going through the activities for the sake of activities, right? And so I think this is a really important piece that all teachers, all educators are teaching literacy across all of their content areas. So I think this was really a great way to put it. I want to open this up now for any questions that anyone may have. Is there anything that anyone needs clarification on as well? Um, Please put it into the chat. The chat is enabled. I made sure of that. So we want to hear from you. We want to hear any insights there. And Sal, just while we're waiting for individuals to either put it in the chat or in the Q&A, is there any comments that you have?
Yes, I just want to make hi everyone. Good morning, good evening, and good afternoon. I just wanted to add that the next webinar in November is going to be how do you develop an integrated STEM unit across the content areas? And we're going to use the next generation science standards, the 3 dimensions, and David is going to carry us through one particular topic, which he's going to mention in a few minutes, what it will be covering. And then we're going to use AI to help us develop this unit. Online, we have some folks that we have worked with before, and it took us around 10 sessions to get that particular task accomplished. And now we are going to be able to do it within a matter of 45 minutes. So that's going to be an exciting webinar. We're going to carry you through. It's going to be developed right in front of you using AI on Zoom on November. What day is it, Kelly?
November 11th at 7 p.m. Eastern Standard Time. And I put the registration link into the chat for everyone as well. But we'll also have it posted on LinkedIn and other places, and we'll be sending out an email as well for everyone.
So David, can you share a little bit about the topic we're going to be covering, the grade level, and how we're going to integrate disciplinary literacy in this particular unit plan?
Surely. We were going to take a look at the genetics piece in the middle school. So that's a fun one, right? That's where we look at the different, the blue and the green eyes, and look at genetics and how they trace. So I think we're going to take, and we're going to use the middle school again, I think, because it's important that we work in between elementary and high school so we can look both before and after. And I think that'll be a really fun one for us. A lot of curricular tie-ins there. And so we're going to take a look at the middle school branch of the genetics piece.
And we're going to be using the backward design. We have a template that we're going to be working from. So basically the duration of the unit, very important. Some of you online have developed units, are developing units on your own now, and are doing a great job. The importance of this is that in New York City, in New York State, they just had the science test. And the teachers were a little taken back for two particular main reasons. One, the students were asked to use technology to work on the test. And two, there was a lot of writing and reading. So that's why we want to make sure, and we've been actually preaching this since 2018, for those schools that have been following us since, did pretty well on the test. For those that started and left us, they have been contacting us to come back to work with us. And the reason that I'm saying this is that this is all something that we provide because we feel really important that children need to connect the dots for their own learning. And this is why we integrate social studies, science, math, literacy, as well as the engineering and math practices. It's very important for the students to relate. If they're going to an ELA class, wow, you know what? We cover something similar in science, and now we know why we need to do that in order to understand the content of science. And they need to learn some skills. So that's what we're going to do on our next webinar. I'm looking forward for all of you to join us. David, you did a great job. Any questions out there?
So I don't see any questions right at the moment, but I'll continue to let that. I did put the next webinar in there. I think the one thing I really just want to mention about this is because the next generation science standards we've been talking about this for years. It's not something that just all of a sudden appeared here. But the relevance of it right now is that we're getting deeper and deeper into the weeds of NGSS, and we're looking now more at the testing and accountability with this. And I think the key component of this is that when we talk about this, we've been talking about integrative STEM for years. And the importance of integrative STEM is the fact that it connects across those content areas. So even though we talk about science, we're using science as a way to think about those hands-on activities, the project-based learning. It gets kids excited about their learning environment. So when we use science as the hook, this is a great opportunity to bring in math, to bring in the reading, the writing, the social studies, the art, all of those disciplines, so that when students start to look at this, they're not just looking at through the lens of a classroom environment. They're starting to connect that to the real world. And what we want students to be able to do is to be those problem solvers and critical thinkers and start to look at their own community on how I can make those improvements there. And so that's what this whole premise is about and why this is so important. And as Sal had said and David said, the next webinar that we're going to focus on is going to start to get a little bit more into the weeds. However, we're going to look at how technology, especially AI and other tools and resources, can help this entire process. What's the number one thing that we say educators don't have enough of? Time. So, right, if we're talking about time, now we're going to talk about how to save you time, how to make this a little bit easier, more manageable, and how we can really start to pull these pieces together. And the other thing to remember about the next generation science standards, wherever you are in the world, these standards help you to link science, engineering, math, reading, writing. So whether you're in the Philippines, in Nepal, in Thailand, wherever you may be, it's an opportunity again to look across the disciplines. And so when we present these webinars, we want to encourage not only the science individuals to be on this, but we want to have your reading and writing teachers, your math teachers, the other content teachers, because this is really important for them to also understand their responsibility and their role and ensuring that students really understand these concepts and start to draw those connections. So I have, so David, you just put a little note in there.
I just put the standard that we're going to be looking at. So you've got a little head start.
And I also just want to encourage everyone too that's on this call. If there are particular topics or areas that you really want us to go deeper into, please let us know. You know, these webinars we're putting together right now, this was based on feedback that we had received. And so this isn't just a one-way street. This goes both ways. We want to hear from you. And if there's questions after the fact, don't hesitate to reach out. I think everyone on this call, you probably have my email. You've probably, I've probably hounded you several times. Don't hesitate to just reach out to me. We have a thank you from Manila there. So excited for our next session. It's great to hear from you as well. David, Sal, any final comments there?
Looking forward to the next one.
Yep, I'm looking forward to the next one. Thank you so much, everyone, for attending, and invite a couple of more of your friends to join in. I think the next one is going to really bring to life what you heard today.
Yeah.
Thank you, David. Thank you, Kelly, for putting this together.
Thank you, everyone. And this is recorded, and I will be sending it out to everyone that did participate in this webinar, as well as putting it on LinkedIn and other places as well. So you'll be able to get that. All right. I want to thank everyone. Have a wonderful morning, afternoon, or evening, and we look forward to seeing you back in November.
All right, guys. Have a great evening.
Bye.
Bye.